So welcome to the 20th lecture in this course on algebraic topology. I'm N J Wildberger at the University of New South Wales, and today we're going to talk about the geometry of surfaces. So last time we proved a very important theorem, one of the central theorems in the subject, that said that any compact connected two-dimensional surface was one of a short list, either a sphere or a sphere with a certain number n cross caps, or a sphere with a certain number of handles. And it's a very nice list, and it's sort of characterized by the Euler number and orientability. So the Euler number chi plus the orientability of the surface determines the surface. Now, it's a very beautiful theorem, but it's also a little bit singular in the sense that when we go to three-dimensional analogs of surfaces, we find no such comparable theorem. The situation currently with three-dimensional manifolds is much more complicated than this. There's nothing even close to such a classification result. Very recently, Perelman established probably important conjecture of Thurston, which sheds a lot of light on some aspects of the classification of three-dimensional manifolds, and also has a lot to do with geometry. But still, nevertheless, we're very far from a nice list where we can see them all. I'll talk a little bit more about the three-dimensional situation later on, but today I'm going to talk a little bit about another interesting aspect of this classification, in that it naturally connects with the three classical geometries. This is something of a surprise, I suppose. So what are the three classical geometries? They are, well, I suppose the most familiar one is the standard Euclidean planar geometry that we learn in school. But there are also two others, so-called non-Euclidean geometries. One of them is called spherical geometry, or elliptic, slightly different, but pretty close. And the third is hyperbolic. So these are three classical geometries, and these last two are usually referred to as non-Euclidean. And it turns out that there's a very strong connection between any two-dimensional surface that on our list and one of these geometries. And I want to discuss that, but it will be impossible for me to introduce these geometries in a very coherent way, so I'll sort of sketch some basic aspects of them. A little bit of an issue is that the way I think about these geometries is quite different from the way most everybody else thinks about them. I think about them in a superior way, but of course that's my opinion. But it means that I'm loath to give you the standard treatment of these things, because I don't really believe in the logical purity of those standard treatments. So I have to say things in perhaps a slightly different way. And the way I'm going to do that is I'm going to concentrate on the symmetries of the geometries and not on the metrical properties. Okay. In the usual modern formulation of these geometries, one thinks of distance and angle as being the most fundamental concepts. However, that's not the way Euclid thought about Euclidean geometry. It's not the way I think about any of these geometries either. So for me, distance and angle are not at all in the picture, and other things are. But I don't want to tell you what those other things are, because that would take me too long. And okay, it's another story. But I can get around that by talking about the symmetries of the three geometries. I can describe things that way. All right. So let us do that, and let's start with Euclidean geometry, just a very quick review. So Euclidean planar geometry is a theory whose symmetries can be built up from reflections in lines. So there's a line, and we have an idea of reflection in the line L. And if you know what reflections are, then essentially you can build up the Euclidean geometry in a reasonable way, because first of all, translations are what you get when you combine two parallel reflections. So if you reflect first in a line like this, and then you reflect in a parallel line, then you get a translation. And if you reflect in two intersecting lines, say you reflect in this line and then reflect in this line, then you get a rotation. So translations and rotations are just composites of these perhaps more fundamental symmetries. All right, good. So now let me remind you that we've already talked about two surfaces on our list that had an obvious Euclidean structure. And maybe I'll first now sort of explain which ones fit into which pattern. So the Euler number being positive, that ends up corresponding to spherical or elliptic geometry. The Euler characteristic being 0 corresponds to Euclidean geometry. And the Euler characteristic negative corresponds to hyperbolic geometry. So which surfaces are where? Well, there are only two surfaces with a positive Euler characteristic. They are the sphere. So chi equals 2 was a sphere, and chi equals 1 was our projective plane. Let's call it P. The chi equals 0 case, there are also only two. They were the torus, which let me call it T, and the Klein bottle, which we might call K. Those are the two surfaces that had an Euler characteristic 0. And all the others have negative Euler characteristic. All the others. Now let me remind you that an n-hold torus, the Euler characteristic was 2 minus 2n. So if n is 1, okay, then we get the ordinary torus with Euler characteristic 0. But for n equals 2, 3, 4, or anything higher, the Euler characteristic will be negative. And for the n cross caps, the Euler characteristic was just 2 minus the number of cross caps. So for one cross cap, we had the projective plane. For two cross caps, we have the Klein bottle. And for anything more than two cross caps, we end up with something with negative Euler characteristic, and so therefore hyperbolic type geometry. All right, so this is the simplest one to talk about. So let me just explain or just remind you about how we thought of the torus and the Klein bottle as essentially having a Euclidean structure. That's maybe a little bit contrary to our usual picture of a torus like that. We usually draw a torus like that. And then it's not so clear what the Euclidean structure is. What does that mean? It looks like points on the outside there will have rather different properties from points on the inside. terms of, they say, their curvature. But we're not talking about the geometry of the torus as embedded in three-dimensional space like this. Okay? That's not what we're talking about. We're talking about another picture that we had. So recall that we obtained a torus by taking the plane, lots of squares, and looking at two translations, say tau 1 and tau 2, in one unit to the right, one unit up, and that then the torus was the plane modded out by the group generated by these two translations. Okay, that's notation. What it really means is that it's a space of orbits. Space of orbits. So I remind you that if you have a point there, then its orbit is going to be all the points that you get by applying tau 1 and tau 2 in all possible ways. And that space of orbits forms a torus. Well, we can think then of the torus as being a square like this, with this side identified with this side, and this side identified with this side. So we don't have to think about the entire plane. We can just think about the square with opposite sides identified, which is pretty well the same thing as thinking about space of orbits. And it's in this way that the torus gets its Euclidean structure, because now we can do geometry on the torus just by doing ordinary geometry on the plane, restricting ourselves to this square. So we just restrict Euclidean geometry to this sort of fundamental domain. That's the fundamental domain. That makes it homogeneous. So the geometry becomes homogeneous, meaning every point looks the same. Every point geometrically is the same. And I also remind you that the Klein-Bottle was a lot like that, but we could use not just two translations, but a translation and a glide reflection. Okay? So maybe we had a tau in this direction, and in this direction, well, we could have a glide reflection. Maybe I'll do it like this. That's let's call it sigma. Sigma is a glide reflection, which is a combination of a translation and a reflection. So that's what that means. It means we're moving one unit in this direction and also at the same time reflecting in this axis. And then the Klein-Bottle becomes the plane modded out by these two different, the group generated by these two different transformations. And a fundamental domain for it is still a square like that. And so it just still has a geometry that you can get by restricting the Euclidean geometry to that square. So whatever theory of trigonometry you have, for example, you can do trigonometry at least locally on a Klein-Bottle or at least locally on a torus. Classical trigonometry or rational trigonometry, whatever one you prefer. All right, so that's our model, and now we want to think about how that same picture kind of extends to, well, just the two surfaces with positive Euler characteristic, and much more interestingly, the whole infinite family of surfaces with negative Euler characteristic. You can describe spherical geometry in terms of also the reflections. So how can one think of spherical geometry? Well, you could just think in terms of having a great circle. So let's say the equator is a great circle. Then there's a well-defined reflection in that great circle. Okay? And that's really just the Euclidean reflection in the ambient three-dimensional space restricted to the sphere. Okay? So given any line or great circle L, there is a reflection in that great circle. No, so that's the reflection in the great circle L. And now if we look at composites of reflections, for example, we have another great circle and they happen to intersect here. Then if you reflect, say, this point first in the line L, and then in the line, let's call it M. So first you go to there, and then you reflect over here. The net effect is to rotate. What ends up happening effectively is that you're rotating around meridian circles centered at the point of intersection of the two great circles. So two reflections, composition of two reflections is rotation. And all of the isometries or all of the symmetries of the situation are products of reflections. And this is all we need in some sense to do geometry, because if we have a little line segment, say we have 2 points A and B, and we want to ask, well, is that line segment the same as some other line segment CD? Right? Suppose we ask that question, is this line segment the same as CD? Now what does the same mean? Well, to a classical geometer, a classical modern geometer, it would mean, is this length the same as this length? Okay. For me, the question would be, is this spherical quadrants the same as that spherical quadrants? But you can avoid that question entirely by simply restating it or reformulating it as the question, is this segment congruent to this segment, in the sense of, is there a symmetry that will map this segment to this segment? Can we reflect this a certain number of times until eventually we get to there? If we can, then they're going to be equal no matter what definition of what measurement system you want to choose. And this is in fact the way Euclid thought about geometry. Right? Euclid did not measure distances and he did not measure angles. He thought about the equality of segments as being an equality of motion. To say this segment was the same as this segment if you could move this segment to this segment using an isometry. Now that's really exactly going back to a classical way of thinking. It's a very good way of thinking. Because we don't have to have a notion of distance, and all we have to do is concentrate on the reflections, which we understand completely. They're very, very simple. So we can say that this segment is equal to this segment without measuring distances or quadrances or whatever. And something else that we can do is we can measure angles, or maybe tangles, turn angles. So for example, suppose we have two great circles or lines meeting like that, and we want to know, well, you know, how do we measure that angle between those two things? Well, what we can certainly do, if that's L and that's M, we can reflect L in M. So we can reflect that, maybe to get L prime. That's the reflection of L in M. And then whatever angle this is going to be, or whatever system you have for measuring angles, this had better be an equal angle. So whether you're measuring classically in terms of pi's, or whether you, as I would prefer, to measure turn angles from 0 to 1, still the statement that this is the same as this is only dependent on understanding reflections. In particular, if we have, say, a certain number of them, 1, 2, 3, 4, 5, 6, 7, 8, that are all equal, going all the way around, then it makes sense to say that those angles or turn angles are all equal, and I'm going to say that they're all going to be equal to 1/8, just as we did in Euclidean geometry. So it doesn't actually involve doesn't really need a measurement system. Now in actual practice, okay, you might be able to divide something up into 8, into 7. You probably are not able to do that accurately. You can only divide something into a full circle into 7 equal pieces approximately. But okay, so you could say it's approximately 1/7 of a turn. Okay, so now these two geometries, well, the geometry of the sphere and the projective plane, they're obviously sort of spherical because the sphere is just what we're talking about. That's obviously has spherical geometry. And the projective plane is really just the sphere. What we call the projective plane is really just the sphere modded out by the antipodal points. Remember? That was one version of the sphere, of the one understanding of the projective plane. It's the sphere sort of modded out by a plus and minus 1. Okay, it's a little bit, actually, to be honest, it's a little bit more complicated than that. There's issues, there's number theoretical issues floating around here. So let me put that in quotes, okay? But it sort of depends on what field you're working over. It's a little bit more complicated than that. But roughly speaking, the projective plane has the spherical geometry that you get from the sphere by essentially taking the upper hemisphere and identifying points on the equator, as we've been doing. All right, so now we get to the most interesting and the most sort of novel aspect of the story, the hyperbolic aspect of it, which is everything else. So most surfaces are hyperbolic. So our usual experience with Euclidean geometry and spherical geometry lets us down. In some sense, the most important geometry is one that's not so familiar to us. Okay. And so I have to tell you now about hyperbolic geometry. But I want to do this very quickly because I don't want to spend several months doing it. But by the way, next year I will start a YouTube series on hyperbolic geometry, or non-Euclidean geometries more generally. And I will tell you many beautiful things about hyperbolic geometry. So if you're wanting to learn hyperbolic geometry, wait for half a year till my YouTube series starts, and you could learn to do it exactly the right way. Okay, so I think the fastest and maybe most familiar way to think about hyperbolic geometry is to think in terms of inversions in circles. So recall that when we were talking about the sphere, we talked about the inversive plane. Remember that? So we had a circle, and we had the idea of inverting in a circle, which sent a point here to another point over here. So x goes to, say, I c of x. And, okay, it had the property that that this quadrant times this quadrant is the quadrants of the circle squared. Or this distance times this distance times this distance is the radius squared. That was inversion. And I remind you that it had a couple of properties, that it sent circles star to circles star, where circle star means circles or lines, and that it preserved angles, or better yet, preserve tangles. So there's a group associated to this. One can then think about the plane, actually the plane together with a point at infinity. We need one extra point at infinity. And you can think about the group generated by all inversions in all circles. That's a big, very nice group called the Mobius group. And so a Mobius group is generated by all inversions in all circles. And what we're just going to look at a more restricted aspect of that Mobius group.
There's only one inversion to circle.
Sorry? Any one circle only has one inversion associated to it, yes. But every circle has an inversion to it, has an inversion associated to it, so you could combine inversions from different circles. All right, so what we're going to do is we're going to fix a circle, and it might as well be the unit circle. Fix the unit circle, let's say in the complex plane, just to be specific. So there's 1 and there's I and so on. And now what we're going to do is we're going to consider inversions in circles, not in this unit circle. Consider inversions in circles which are perpendicular to our unit circle. Let's give our unit circle a name, say C unit. There's C unit, C unit. Okay, so what does that look like? I'm talking about a circle which meets our unit circle perpendicularly. So that would be one example. That would be a smaller example. A bigger example would be this one. And another example would be this one. So maybe I should say circle star. We're also allowing circles of infinite radius, i.e. lines, as part of the story. So all of these are circles which meet our C sub u perpendicularly. And the crucial thing is to observe what happens when you invert in one of these circles. What happens? Suppose we invert in this circle here. Well, these 2 points are fixed. And this circle, the unit circle, must go to another circle. So it must go to another circle that also goes through those 2 points. Because these points are fixed. Well, there are lots of circles that go through these 2 points, but there's only one that's perpendicular to our given circle. Because we said that it preserves angles or tangles. So this perpendicularity has to be preserved, and that means that this inversion sends C sub u to C sub u. So each sends C sub u to C sub u. So let's see what it's doing here. So it's taking a point x there, and it's inverting it. So it would be maybe x prime. That point gets to x prime. And this point here, call it y, that would go to y prime. And this point here, z, well, that would be inverted. That would go to point z prime. But since the boundary circle stays where it is, the inside of the circle maps to another point, or the inside of the circle maps to the inside. So each sends C sub u to C sub u and sends the inside of C sub u to the inside of C sub u. Actually, it's a bijection on the inside. Because you can invert just by doing it again. Okay, and hyperbolic geometry is what you get when you consider these to be the reflections. Okay, so hyperbolic geometry is what you get when, well, this is a particular model of it. There are other models. This is the Beltrami Poincare model. Beltrami Poincare disk model, maybe one should say. So the idea is the geometry, the space is just the interior. So that's the hyperbolic plane. And these inversions are the reflections. So the points are the inside of C sub u. The lines in this geometry are these arcs of circles perpendicular to the boundary. Circular arcs perpendicular to C sub u. And the reflections are these inversions in the lines in the circles perpendicular to C sub u, i.e. what we're calling lines. So let's see if we can draw a picture or two. So this is C sub u. And let's do a little bit of geometry. So here's a point A, and here's another point B. And suppose I want to draw the line through A and B. I would then have to look for a circle which is going through A and B, which is perpendicular to the boundary. Okay, so it's not that easy to draw it freehand. So there. All right, so that's part of a circle that, let's say, meets C sub u perpendicularly. So that's the line through A and B. Suppose we have another point over here, say C. Then we can also draw the line through A and C. It's going to be some circle like this. And the line through C and B. Okay, maybe something like that. Okay, they shouldn't be crossing like this. They should just all right, so this is what we have inside here is a triangle. That's a hyperbolic triangle. Triangle through A, B, and C. Now, what about measurement? Well, I said we're not going to use distance or angle, and I'm not going to tell you what quadrants and spread are either. So we'll just talk in terms of this congruence. So suppose we have, let me make 2 points which are a little bit closer to each other. So suppose this is A and this is B, and I want to make an equal segment to this one on this side. Okay, suppose I just want to make an equal segment over here. How would I construct this point here? Well, I'd want to reflect in this point here, and I want to reflect, well, there might be lots of circles going through there, but I'd want to choose a circle that goes through there perpendicularly. Okay, so I would find a circle that goes through B perpendicularly, and perpendicular is in our usual sense of perpendicular here, just the familiar sense. So we find such a circle, or a line actually, which happens to go through B perpendicularly, and then we reflect A in this circle. In other words, we invert. Okay, so there's its center somewhere. If we invert in this circle, we'd get this point here. That's an isometry, so it's going to keep B fixed. So it's going to ensure that this segment and this segment are equal. So in this way, we could continue. We could make a ruler. We could find another point D, so that that's also the same length, or not same length, congruent. And we could keep going. And what you'd find is that as we approached here, the points started getting closer and closer together. And we wouldn't get to the boundary. There would be an infinite sequence of points as we approach there, or in fact as we approached here as well. They just get closer and closer, and there's an infinite sequence of them. So despite appearances, there's actually an infinite number, or that length or quadrants of that line is infinite, no matter how you're going to measure it. And an aspect of this is that there's a lot of room very close to the boundary. The boundary itself is actually not part of the space. It's sort of at infinity in the usual story. And sort of in a little narrow strip, there's actually a lot of room in this hyperbolic geometry. All right, so drawing circles like this and inverting is a little bit, it's pleasant geometrically, but if you want to do calculations, for that there's also an analytic formula, analytic representation of our reflections. And for that we'll use our picture of C sub u as being inside the complex plane. So if we choose any point z naught, well, maybe I'll use w. Choose any point w inside there. Then fix w in h, our hyperbolic plane. So that's the inside of the disk. And then consider the transformation phi of z equals z minus w over 1 minus w bar times z. That's a special case of the formula, of the more general kind of formula, az plus b over cz plus d. That's called a general fractional linear transformation, or a Mobius transformation. That's a fractional linear transformation. Fractional linear transformation, or Mobius transformation. And this is a special kind, and the claim is that this transformation sends the disk to itself. And it's what you get when you look at this circle kind of transformation in coordinates. If you actually drew a circle and experimented, you could get it into this form, actually plus a rotation. So you could also take this thing here and you could also rotate everything by a rotation of the plane. Say by multiplying by the complex number E of h, a number on the unit circle. All right, so we've seen how we could maybe make a ruler along a line. Another interesting thing to be able to do is to replicate angles. So suppose that we have a point and we have two lines going through that point. So that one and say that one. And we're interested in that angle, or maybe I'll call it a tangle. That might be 1/8 of the way around, for example. So we could replicate that tangle, whatever its measurement is, whether you're measuring in radians or tangles or degrees. Whatever it is, we can replicate it simply by reflecting. For example, we could reflect, say, the line L in the line M. Okay? So if we reflect in M, just as we did in the Euclidean case, we would get another line L prime.
By reflection, inversion.
Reflection is the same as inversion, yes. So from now on, I prefer to say reflection because that's sort of the geometrical what we're thinking, but it's actually an inversion in this circle here. So if you invert this circle, well, then this circle stays where it is, and this circle goes to another circle and goes to that circle there. And then it'll be a fact that this angle or turn angle will be the same as the one you've just got. In particular, you could keep going and you could do it again. Let's say and maybe one more time. How many is that altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so if this was carefully chosen, then perhaps we could go all the way around 10 times and we'd be back to where we started. And then we could assert that, well, let's use the tangle notation and say that that's a tangle of 1/10. So in this way we can, in some sense, measure angles or tangles, and this is a kind of a crude way of measuring congruence of segments. All right, so now we've got the ingredients of how to show you how the other two-dimensional surfaces appear in hyperbolic geometry. Okay, so that's what we're going to do next time. I'm going to have a look at two very special cases. We're going to look at the two-hole torus and the three cross-caps surface. And we're going to try to visualize them as somehow sitting inside hyperbolic space. So I'll see you then.